Hello everyone and welcome to Calculus BC. In today's episode we're going to be discussing volumes by shells. Now this is going to be the last volume method that we learn in Calculus AB or BC. And so I'm going to go and just recap a couple things about the previous rotational volumes that we know of, and then we'll see why shells is also an important method. So in the past, if I gave you two functions like say y equals x and y equals x squared, we're not going to find the volume of this, but and I had you rotate it somehow, right? So this would be the parabola, and this would be the line. If I had you rotating this thing about the x-axis, right? About the x-axis, what would happen is you would end up, and this would be a hollow figure, but you would have these pieces extending up outwards and then rotating, right? And so this was pretty clear about how I was going to rotate this thing. We had that idea about the dentist and the dental assistant, where the dentist would integrate the thing furthest from him, the dental assistant would come in and burrow out the volume that we didn't need. The reason why this method worked here is because there was a clear top function and a clear bottom function, right? And that is what made rotation around the x-axis really, really, really simple. Now, if I had you guys do this thing dy, right? If I had you guys do this thing dy, whoops, change color back. If I had you guys do this thing dy, again, I believe it would have been equally as easy because of the notion, right? If I had you rotate it this way, now we have this, we have the dentist going for the curve this time because the curve is furthest away. And then the dental assistant would have knocked out the line. And the reason why this one would have been equally easy is because in this case, a dy integral would have had a clear right function and a clear left function. In other words, in both cases, it was clear which was further away and which one was closer, right? Regardless of dx versus dy. So this would have been our dx integral, this would have been our dy integral, but either way, a far function and a close function are laid bare to see. So far function and close function are obvious. But of course, we can't always rely on the notion of a far function and a close function to be laid bare for us to see. So this is when shells becomes part of our lives. So I will show you an example. And I know what you're thinking. You might be thinking, why would we ever not know which function was further away? We always know which function is further away. We always know which function is closer. Well, how about if I gave you something that looked like this? If I said f of x is equal to 2x squared minus x cubed. Now, this is going to take a little bit of suspension of belief here. I need you to, and if you don't believe me, totally cool. Just pause the video, graph that thing on Desmos or something like that. But I hope you will all take me on my word that this graph will look like that. At least on the right side. So from here, I hope you guys will believe me. His x-intercepts are at 0 and 2. Now this time, we're going to spin him about the y-axis. And I hope you can all see right now what the conundrum of that is. Because now, if I'm going to rotate this to about the y-axis, there is a clear right side and a clear left side, but they're all part of the same function. So, I got a couple options. I could, if I really wanted to use the washers method or for the hollow figures, I'd have to make a piecewise function to find out where he breaks at the maximum and do a left side integral and a right side integral, subtract the left side from the right side, and do it dy style. That would involve also getting the x by itself here, which is going to be really, really hard. So I don't think that's a direction that I want to go. Nevertheless, I want to rotate this thing about the y-axis so that what I end up with at the end of the day is going to be an image that cycles around like this. And barring any artistic ability, it's going to cycle around like that, and almost look like one of those sponge cakes from that you can get at the supermarket that you put strawberries and stuff into. I forgot the shortcake, and you could do that. So from here, how do we do this? Well, what I'm going to do is I'm going to first eliminate all those figures right there, and I'm going to introduce you guys to a cylindrical shell. Now, let's talk about what a shell is. A shell is really just a hollow figure that holds something, right? And so depending on what it holds, it could be solid or it could be hollow, and that will depend on the thickness of the shell, right? We have egg shells, right? Otherwise empty. They hold eggs. We have heroes in a half shell, right? Those half shells hold heroes. 4 of them, right? So if you understand that reference. So we're going to construct a bunch of those cylindrical shells right now. And so how do we do that? Well, to construct a cylindrical shell, we're going to first evaluate what the surface area of a cylindrical shell would be. Well, when we look at a surface area of a shell, or a cylinder, so cylinder, surface area. Back in integrated 2, you learned that it's 2 pi r squared for the 2 circles plus 2 pi r h. This is the piece we want to pay attention to because we're going to be constructing a bunch of cylinder shells inside this figure. So the way I'm going to do this is I'm going to go ahead and construct, I'll change colors here. I'm going to go ahead and construct a rectangle inside the figure. Now notice how not all of the rectangles are going to be the same height. Right? And so each rectangle will have a different height. The height of that rectangle is dependent on, I'll give you guys a couple seconds to think about it. It is dependent on the value of the function at that point in time. The 2 pi is constant. The radius will extend from the y-axis and interact with its own respective shell. Now from here, each radius is not the same length because the radius is only correspondent to the rectangle that it touches. So if I was to do this radius right here, this radius would be correspondent to that super small rectangle. But this radius here in red will be correspondent to this super small rectangle on the right side. And so since each radius has a different value, but it's a different horizontal value, a horizontal value that varies at all times, well, that radius is going to have a value of x. And what we're going to do is we're going to do a summation of all of those cylindrical shells. Now, I haven't talked about volume yet. Right now, I'm just getting surface area. This is going to be 2 pi x sub I star f of x sub I star. We talked about the x sub I star in the last video. It's the ith rectangle or the index rectangle at that moment in time. But right now what I'm creating is I'm creating just a super hollow thing. But if I'm going to create volume, right, I need to have a thickness to that shell. Well, the thickness will be dependent on how thick each rectangle is at that moment in time. Well, how thick is each rectangle? Well, each rectangle is as thick as it can be based on its change in x. And so that will be delta x for my thickness. Now that I've got a surface area that I'm working with, if I just work with this surface area and multiply it by a third dimension, which is the thickness, now this is going to be my volume. This is my volume of one of the shells. But I'm not going to get the volume of one of the shells. I'm going to do a summation of this volume here. So from I equals 1 to n, 2 pi is a constant, x sub I star, f of x sub I star, delta x. And if I take the limit as the number of rectangles goes to infinity, we've seen this movie before. This turns into a summation integral from a to b. Let's see, it's going to be x times f of x. Delta x gets so small it becomes an infinitesimally small change in x dx. And then the 2 pi can hang out on the outside. And this is our volume via shells formula. Type that in. Get that in our notes. And here we go. So I'll give you a second to copy that down. I'll be right back with some example problems. I'll be right back. So why don't we begin with the function that we couldn't integrate from before? So let's go and take a look at this guy. We're going to rotate him about the y-axis. All right, now, from here, one thing I'm hoping you noticed during the derivation of the volume formula by shells is that unlike the other two, which are with your intuition in terms of the fact that when you rotate about the x-axis, it's a dx integral. When you rotate about the y-axis, it's a dy integral. The shell is opposite. We are rotating this thing about the y-axis, and yet the radius is in terms of x, and the height of the function is dependent on f of x. So when this is rotated about the y-axis, please write this down. This is a dx integral, and that is not a mistake. In fact, the mistake will be making it a dy integral, because that's what we're used to from Calc AB. So please make sure you are cautious about that. About the y-axis on a shell, dx integral, which means 0 to 2 are in fact my limits of integration. So 2 pi here, my radius is going to be some value of x, so x, and then my height is going to be 2x squared minus x cubed dx. And then let's distribute this guy in. 2x cubed minus x to the fourth dx. Have not done any calculus yet. So now I'm going to go ahead and get this integral started here. So I'm going to go ahead and get this to be x to the fourth over 4 with a 2 minus x to the fifth over 5 on 0 to 2. Please don't forget that 2 pi hanging out on the outside. So what I've got is 2 pi times, looks like 1/2 2 to the fourth minus 2 to the fifth over 5. Put him in parentheses. Minus, luckily the 0 is going to make them all turn to nothing, so we're all good. So ultimately what this turns into is it turns into 2 pi times, looks like that's going to become a 16, so 16 over 2. 16 over 2 minus 32 over 5. And please feel free not to simplify that if you encounter that on a quiz. Otherwise, it's just common denominator work. Wouldn't be too hard. 8, so then that would be 40 over 5 minus 32 over 5 times 2 pi. So it looks like 8 pi, oops, not 8. 8 over 5 times 2 pi. So I'm getting 16 pi over 5. But as always, please feel free not to simplify those on quizzes. Okay, let's take a look at another example. Let's take a look at another example. So we'll do a pretty easy one. Just coming out the gate here, y equals x sine x. We'll rotate him about the y-axis on 0 to pi. So as always with these volume problems, I like to graph them. Sine looks like this from 0 to pi. Now if I'm rotating them about the y-axis, that makes this a dx integral. If you want to, write that down before you initiate a shells problem. And again, it's a shells problem because there's no clear left or right side on this one, right? Again, I don't want to make this a all right, let's start this second example here. I'm going to just have us rotate y equals sine x. And we're going to rotate him on the interval 0 to pi about the y-axis. So let's go ahead and draw him out. I like to draw these volume problems. So that's pi right there. We're rotating him about the y-axis, which makes this a dx integral because we're doing shells. And again, why is shells important or necessary for this problem? I'm not going to make a piecewise function out of this. Forget that. I'm going to go ahead and just rotate him because we have a technique for it. So from here, what am I going to do? I have to really visualize this. This is going to be some radius with some rectangle, right? So my radius is x long, and my height of the shell, of the rectangular shell, is being based off of the height of the function at that moment in time. So I'll go ahead and do the integral from 0 to pi. My radius is x. My height is sine x dx. And right now, this is about as far as we can go with this problem. At this point, you would plug it into a calculator and you would go for it. In a future video, I will show you exactly how to deal with this type of integral by hand. It will be a concept that we cover in BC, but as long as we have this set up, then we will be golden in terms of this particular rotational problem. So I did just want to show you the setup for that one. That one's pretty fast. I do want to show you guys that shells actually can be used for other shapes. I mean, so the ultimate goal of learning shells is to show you how to use this to find the volume of something where the top, bottom, or left, right isn't clear. But at the end of the day, the ultimate goal is to make you sure that you are flexible of mind. That way you can apply shells even when you would have otherwise used a different tactic. But if you want something more streamlined, more hardlined, then keep shells for the for the ones that aren't clear in terms of top, bottom, left, or right, and then use your discs and washers for where you can see the top, bottom, or left or right. Especially, we don't have an expectation that you're going to be that good when you first start off. You're just beginning. So for now, just get used to the notion of shells, and then eventually you'll learn how to adapt them into different methods here. So let's do a problem where if I have y equals x squared, y equals x. Now we did this one at the very beginning, and we'll rotate them about the y-axis. Now ordinarily, we wouldn't use shells here, right? Ordinarily, so let's go old style. Old style. And then I'll copy it again for new style. So new style here. Okay. More or less the same. Our limits of integration are, 1 to 1. Or 0 to 1, sorry. 0 to 1. So let's go and do this old style. We're going to rotate about the y-axis both times. So in the old style, because we're going to rotate this thing about the y-axis, this is actually a dy integral, right? Because we're about to initiate a washers method on this thing. So I got to replace these guys. So I got to say now that x is equal to rad y and x is equal to y, and my limits of integration are still from 0 to 1, but they're pulling from the y coordinates of 0 to 1 this time. So if I was to do this, I would get the integral from 0 to 1 pi, right? And then I would do my dentist and dental assistant deal. So from here, the dentist here integrates the furthest thing away from him. That's going to be the rad y. He's being squared dy. And then the dental assistant comes in and says, whoa, back up, bucko. And he integrates the thing closest to him. So that's going to be, again, from 0 to 1 of just y dy. And those things are being subtracted. So what you end up with is pi integral 0 to 1 of y minus, that should be squared. So y minus y squared dy. So now I'm going to go ahead and integrate this thing. So what I get is I get y squared over 2 minus y cubed over 3 times pi. And that's going to be evaluated on 0 to 1. And so what I get is I get 1/2 minus 1/3, which is going to be, let's see here, 3/6 minus 2/6, so 1/6 times pi, so pi over 6. That is the area, or the volume, sorry, that is the volume of this shape when it is rotated about the y-axis. So that's the old style, right? That's the old style. Now, let's take a look at the new style. If I was to do this dy, or if I was to do this about the y-axis, this is actually a dx integral, right? Which means I can leave my functions as they are. I can call them y equals x squared, y equals x. My limits of integration still come from the x values here. And so now from here, if I'm going to rotate this thing about the y-axis, what I'm going to do is I'm going to go ahead and have a rectangle right here, right, with a correspondent radius. Now the rectangle is only going to be that tall because it's going to be the space that exists in between the line and the curve. So what that means is my integral will be 2 pi integral from 0 to 1. Again, limits of integration coming from the x. My radius is x, but my height is going to be line minus curve dx. And so now if I go ahead and distribute, I get x squared minus x cubed on 0 to 1. Don't forget the 2 pi. So let's go ahead and see what happens when we integrate this thing. I'm going to get x cubed over 3 minus x to the 4th over 4 on 0 to 1. Luckily, the zeros are going to go away. I end up with 1/3 minus 1/4. I'm hoping you can kind of see the connection here with a 2 pi. That makes these things pi over 12, right? So that means, what is that, 4 pi over 12 minus 3 pi over 12? Oh, it's not 4 pi, just 4 over 12 and 3 over 12. I got a little ahead of myself there. Sorry about that. Get rid of those pi's right now. For some reason, I was thinking of sum and difference formula right there. Whoops. 1/12. All over the place now. Goodbye. Pi over 6, and you get the same volume. And so if you ever want to try shells on what otherwise would be a washer's method, feel free to. Experiment. Play with it a little bit. I'm going to do a couple more examples, and then we'll be good. Of course, it wouldn't be volume unless we did an off-axis rotation. So we'll do an off-axis shell for the last couple of examples here. I do want to do a dy integral with you guys. And so when it comes to the dy, it's going to be parallel with the x-axis this time, right? So remember, it's opposite of our intuition. So if I do x equals y minus 1 squared, and then x equals y plus 1, and we're going to rotate this thing about the line y equals -2. And so let's take a look at what this looks like visually. Sideways parabola shifted up by 1, so he's going to look kind of like this. That. Y plus 1 is going to be the same. If you're not sure, it's going to be the same as y equals x minus 1. So he's just going to be a line that looks like, oh, darn it, straighter than that. It looks like that. Okay. Now, I'm going to rotate this dude about the line y equals -2. So that's going to be like down here. Now, because I'm rotating this thing with something that's parallel to the x-axis, this is not a dx integral. It's dy, because we're working with shells this time. Our radius is dependent on the y value now, okay? So from here, how do we do this? Well, first of all, I want to go ahead and find out the limits of integration first. And the limits of integration are going to happen if I let y plus 1 equal y minus 1 squared. And so if you look really, really hard, you might be able to tell that if y equals 0, that would be 1. And the other one that's a little harder to tell, and you might have to actually factor this one to figure it out, the other one that would be hard would be like 3. Okay? Because 3 plus 1 would be 4. 3 minus 1 is 2, but 2 squared is 4. So that's going to be what gets me my limits of integration here, 0 and 3. Okay, so 2 pi integral from 0 to 3. Now from here, because my rotational axis is below the desired area, I've got to remember that when I extend my radius, it's going to extend from the axis, right? It's going to be some value of y, right? This is some value of y. The problem is that I'm not rotating this thing about the x-axis. I'm rotating this thing about something that is 2 steps below the x-axis. So I've got to rotate this thing all the way here. So how do I get there? Well, that is an addition of 2 spaces, right? So my radius is actually going to be y plus 2. Or if you really want to look at it in terms of a subtraction, because we always tend to subtract, especially when the rotational axis is above, it's really y minus -2. Either way, you end up in the same spot. So I'll just go ahead and fix it up and call it y plus 2. So that's going to be how long my radius is. And now what's going to happen is the rectangle that is formed, the rectangle that is formed is going to be the distance between the line and the curve. So that's where I'm going to get my height from. So it's going to be times y plus 1 minus y minus 1 squared dy. So if we were to actually integrate this thing, what we would get is we would get this guy to become y squared minus 2y plus 1. And it would be y plus 1 minus y squared plus 2y minus 1, all times y plus 2, integral from 0 to 3, 2 pi. So let's go ahead and simplify some terms here. So these guys are going to go away. I end up with negative y squared plus, actually I'll call them 3y rather, 3y minus y squared times y plus 2 dy, and integral from 0 to 3. So a lot of algebra involved here, but that's okay. So we're going to get 3y squared minus y cubed plus 6y minus 2y squared dy. So a lot of algebra going on here, but that's okay. So we're going to go ahead and get negative y cubed plus y squared plus 6y dy, integral from 0 to 3, 2 pi here. Now we're finally ready to do some calculus, right? Now we're ready to finally do some integration. So I'm going to get negative y to the 4th over 4 plus y cubed over 3 plus, looks like 3y squared on the interval from 0 to 3. Don't forget the 2 pi hanging out on the outside. So now I'll go ahead and evaluate this thing. So I'll get 2 pi. Looks like I'm going to get negative 3 to the 4th over 4 plus 3 cubed over 3 plus 3 times 3 squared. Luckily, the minus 0 makes it all go away. So it looks like we've got negative 81 over 4 plus, looks like 27 over 3 is 9 plus, looks like that's going to be 9, so 27 here times 2 pi. So now 9 plus 27 is going to be 36. Plus negative 81 over 4. So if I got a common denominator here, I'll just multiply the top and bottom by 4. Looks like that's going to be 36 and 4 is 4, 2, 12, 144. So 144 over 4 plus negative 81 over 4. Subtracting those two gives me 63 over 4 times 2 pi. So what I end up getting is 63 pi over 2 as my volume of this shape right here. So a little bit algebra intensive, a lot of multiplication, plenty of places where you can make a mistake, but definitely still doable. Okay, let's go and take care of one last one here, another off-axis shell. I'll go ahead and just set this one up because, again, it's going to involve a sine function, and we don't really have a mechanism for that just yet. But I'll go ahead and give you guys y equals sine x on the interval from 0 to pi. And we're going to rotate this thing about the line x equals 4. And so again, just graph it. Just graph it. So from here, this is 0 to pi. Pi is about 3.14, so hopefully the line x equals 4 being out here makes sense to you. We're rotating it about him, rotating about something parallel to the y-axis. That makes this thing a dx integral. So I'll go ahead and set this guy up from 0 to pi with a 2 pi on the outside. The question is the radius. The radius is going to be difficult. So remember, the radius is going to extend from here, right? So it's actually going to be, and I'll actually draw it up here so it makes more sense. The distance here is actually 4, right? But we don't want all of that 4. We're going to backtrack it so that it ends up right here. So the question is how much is this horizontal orange distance? Well, that's going to be 4 minus this value here. And that value right there is going to vary. So that's going to be x. So my radius is 4 minus x. My height still comes from sine. Slap on a dx for thickness, and then just plug it into a calculator and you'd be all set. So the notion of when the rotational axis is in front or in back or on top or on bottom still plays out exactly like it did in disks and washers, where you end up having to either add a value or do number minus that x value. So hopefully that makes enough sense. As always, please leave questions or comments in the comments area. I will see you all in the next episode.